Welcome to Lecture 7.2, Looping, for Introduction to Programming in Mechanical Engineering. By the end of this lecture video, you will have an understanding of what for loops are, how to write a for loop, applying a for loop to studying the friction forces on a system, what while loops are, how to write a while loop, and applying a while loop to iteratively loading a bridge model. This slide, the table of contents, contains hyperlinks to each of the sections to make the downloaded PDF easy to navigate. When loops were first introduced in this course, we gave the following definition. The program executes one or more operations repeatedly until a termination condition is met. We'll build on this definition in this lecture with the two types of loops in MATLAB. For loops iterate through a vector until reaching the end. They're a great way when you already know the total number of iterations for the loop to perform. For example, if you have an array whose size you already know and you want to perform some operation on it. We used a pack of hot dogs to illustrate this back in Lecture 2.2. Structurally, the for and end keywords are used as wrappers for the loop. The variable var here is what changes its value with each iteration of the loop, and it does so according to the contents of the vector on the right-hand side of the equal sign. Within the loop operations execute with each iteration, and they often utilize the looping variable in some way to change what it does each time. Let's inspect this with a simple example. First, let's set up the structure of the for loop using the for and end keywords. Then declare the variable to change each iteration. Here, I call it looping variable. Then define the array of values for that variable to adopt. In this case, I've chosen some arbitrary array 1, 5, 3, 9, and 100 to illustrate the underlying functionality. Then define the inner loop operation, which in this case is just to print out the value of the variable in this case. So when this code runs, iteration 1 produces the text looping variable equals 1. Iteration 2 says it equals 5, then the third says it equals 3, fourth says it equals 9, and the fifth says it equals 100. And at this point, the looping variable has reached the end of the array, so the loop terminates. Most often, loops are used with an indexing variable that is used to access different elements of one or more arrays inside of the loop. For example, let's define a simple x linspace array, and then set up a for loop with the variable index equal to the array 1 colon length of x. With each iteration of the loop, the index variable here will take a value from 1 to the length of x. The loop operation inside is again just simply printing out the value for illustration purposes, but we'll see a more complex example in a minute. The crucial part of this is that by using the variable index, we can access and print a different element from x with each iteration. The previous loop's results are printed out in the following, where each element of the array x was accessed individually. Consider the following block on an inclined plane. These three equations describing the weight vector, the normal force, and the static or kinetic friction on the block allow us to simulate the net forces on the block for any value of the incline angle phi. Before we actually write any of the code, let's just review how static friction works, because it's not always at its maximum theoretical value, which is what is given by the previous equation. It always balances the other forces present in its net magnitude until its maximum value is reached, at which point the object begins to slide. In code, we'll capture this by including a check against the static friction threshold to accurately represent the force's value. First, let's define the coefficients of static and kinetic friction. I got these numbers off of the internet, but the specific values don't really matter too much. Then let's define the weight vector of the block. We know that the weight always points in the negative y direction, so its x component should be 0. Then let's add in functions for the normal and the static and kinetic friction forces, which only differ by the coefficient that is used. Finally, prepare an array of incline angles, phi, which goes from 0 to 90 to give us the entire possible range for the incline angle. Now we can actually set up the loop to evaluate the forces at each of these angles. First, let's set up the structure of the for loop with an index variable I, which will iterate from 1 to the number of elements in the phi array. Then let's use the function we wrote previously to evaluate the normal force at the current angle by using the index I to access the current value of the phi array. Similarly, use the function for the static friction to evaluate the highest possible force that the friction can impart. Remember, this is not necessarily the actual force that is imparted. To address that, we compare the force of the weight directed down the incline against the maximum static friction force, which is directed up the incline. This ratio tells us whether the block should slide or not. So we can set up an if statement here where the block remains stationary if the ratio we just calculated remains at or below 1. We can justify that to ourselves by thinking about the equation. In the numerator, we have the magnitude of the block's weight, which is directed down the incline. In the denominator, we have the friction force, which points up the incline. If the fraction is less than or equal to 1, then the maximum force of static friction is still greater than the force that is being applied by gravity down the incline. On the flip side, if the force ratio is above 1, it means that the weight directed down the incline is greater than the theoretical maximum value of the friction force keeping it in place. Therefore, the block starts to slide, which we will denote using the else keyword. Now, if the block isn't actually sliding, then we have to recalculate the static friction force to match the actual value by using the previously calculated ratio, and we set the net force vector to 0, 0. The reason we can do this is that we know that the block remains stationary, and therefore there should be no net force on the block. However, if the block does begin to slide, then we have to re-evaluate the friction force by using the function for kinetic friction, which we wrote earlier, and then we add up all three of the forces to get the net force on the block. After evaluating the forces at each angle, the following code is used to plot the net forces in both x and y directions as functions of the angle phi. We've seen these commands before, so I won't go through them again. Note that both of the x and y forces remain at 0 until they suddenly jump to non-zero values. That jump is the point at which the block begins to slide. It's caused by the fact that the coefficient of kinetic friction is lower than the coefficient of static friction, meaning that once the block slides, the force that is imparted by kinetic friction is less than the maximum value of static friction, and therefore there is not a continuous line from 0 to non-zero values. We can now analyze the value of phi at which that jump actually happens. To start, let's evaluate a logical array that returns which elements in the sum forces array are equal to the 0 vector. We do that by using the most interior conditional in this line, checking that sum forces equals 0. This gives an array of which elements are equal to the 0 vector. Then the not command inverts all of that so that each element indicates whether each force is non-zero. The any command on the outside is used with the index 2 to execute the OR operation along each row in that array, which is then used to collapse the two-column logical array into one column. This creates a single array that specifies whether the net force on the block at angle index I is 0 or not. This logical array can then be used to extract values from phi by using it as an index. Only the elements of phi where the array evaluates to true are extracted. So, in other words, the slipping angles array contains only the angles where the block is slipping. Finally, to extract just the first element of the array, we use the index 1, because that specifies the point at which the block begins to slip down the inclined plane. In this example, we find that the slipping point is 26.5 degrees plus or minus a little bit. Now, unlike for loops, which have a specified array to iterate through, while loops iterate until the associated conditional statement no longer evaluates to true. They are best used when the number of iterations for the loop is not already known. This could arise if, for example, you have a trigger variable or some threshold to meet for iteration varying residuals. In a similar format to for loops, the while and the end keywords are used as wrappers for the loop. The while keyword is followed by a conditional statement, which is evaluated at the start of each iteration in the loop. The loop only continues if that statement evaluates to true. Inside of the loop are operations which execute and update a variable that gets reconsidered in the conditional statement on each iteration. To illustrate while loop usage, the MathWorks documentation writes the factorial operation from math as an example of a good case. First, let's define the number on which to operate. In this case, we'll just use 10. Then we set up a variable to represent the next number in the operation, which is 9. And of course, we need a variable to store the result of the overall operation. Then we can set up a general structure for the while loop, where the condition is that next number is greater than 1, as that is the end of the actual factorial operation in math. Then within the loop, we update the factorial result by multiplying by the next number, and then decrementing next number by 1. And finally, we print the result to screen, which shows that 10 factorial equals 3,628,800, which is the correct answer. Now, to further demonstrate the utility of while loops, we'll iteratively load the following truss structure until it reaches its failure point. Now, just as a disclaimer, this demonstration will not cover how to actually evaluate the truss, as that is a topic for another class. But as a hint, it's just a system of equations, which is something we have covered. For this demo, we'll make use of a quote-unquote black box function that encapsulates the evaluation process. That way, we can focus on working with the results of that function without needing to see how it actually works. So, first, let's set up the constants of the problem, which in this case are the yield stress and the cross-sectional area. These numbers are somewhat arbitrary. Similarly, I just got them off the internet or made them up in my head. Then let's initialize the stress vector for each member of the bridge, as well as an initial value for the applied load on the structure, which is 0, because we want to increase the force until it breaks. Then we set up the structure of the while loop with the condition that the maximum value of the internal stresses should be less than the yield stress. This check allows the force to be increased until one or more members exceeds that limit. Then we can actually fill in the loop operations by first incrementing the force value and then calling our black box function that evaluates the bridge and returns the internal stresses of each member. So this code block would determine the force at which the truss exceeds its yield stress. It can actually be wrapped up into an outer for loop to optimize the structure and to determine the best truss. So this block of code here iterates the internal angle in the truss and evaluates the maximum force and performance of the truss at each of those angles. Ultimately, a combination of a for and a while loop enables a thorough analysis of the truss design, which yields a figure like this one, where it's clear to see where the bridge performs best at the peak of the red curve. And just to be extra clear, this graph is not an exact representation of the demo from this lecture, but it was taken from a more complex version of the same thing, so all of the principles are applied here. In summary, for loops are used to iterate through a defined array and to execute some operation a set number of times. The for and the end keywords surrounding looping operations, which execute for each value in an array defined at the start. Often, the looping variable is used as an index for accessing arrays. Then by utilizing custom functions to evaluate the applied friction and the normal forces at any given angle, the for loop enables you to analyze the forces on a block at each angle of an inclined plane. Then while loops are used to iterate for an undefined number of times by using a trigger condition of some kind. The while and the end keywords surround the looping operations so long as the given conditional statement evaluates to true at the start of each iteration. By using a function that evaluates the stresses within the bridge given an applied force, the while loop enables you to increment the load until the stress exceeds its limit.